Hi, I'm Dr. J, and this is a video about regression. And in particular, it's a video about f-tests within the context of regression. As usual, up above, there's a link to the playlist all about regression, and down below, there's a link to a PDF version of these slides. All right, in a previous video, we talked about ANOVA, and ANOVA was a special case of this general type of statistical methodology called an f-test. In this video, we're going to show the use of this general methodology through two examples, and we're going to show sort of all the mathematical detail about constructing these f-tests. So f-tests generally are looking at composite alternatives. I'm not going to focus that on this video, but instead I'm going to think about comparing a full and a reduced model. So in the previous video about ANOVA, our full model had a different mean for each group, and our reduced model had a common mean for all the groups. Right? So that's the kind of comparison that I'm interested in doing. And now the way that an f-test works is that it basically is trying to describe the amount of variability that's left over between those two models. So if we had a reduced model, say that had a common mean for all the groups, there's some variability that's left over. Now when we add on a different mean for each group, we have less variability. That is the variability reduced enough that we should prefer that model with different means or that full model over the reduced model? Let's start to fix ideas by considering the ANOVA model we talked about last time. Right? This said we had observations that were grouped. The groups here are different J's. We have capital J groups. Each group has its own mu J mean, and then the observations around that are independent, normally distributed, and have a constant variance, sigma squared. And our ANOVA assumption said, hey, those mu J's actually, the null model says they're all the same, it's just some value mu, and the alternative says that at least one of the means is different from another. All right, so really I want to think about this, as I did in the previous video, about two different models. The first model just says that data are IID with a common mean mu and otherwise the same assumptions. And the alternative says that no, in fact, each different mean for the different groups, or each group has its own mean. Okay, and so we can think about that alternative hypothesis model as being a full model. It's fuller in that sense that it has more flexibility, each group having its own mean. In contrast, the null model is the reduced model because it only has a single mean for each, a single mean for all of the groups. Now, in the previous video, we saw that we could use an f-test to compare models of this type, but more generally, anytime we have a full and reduced model, we can use an f-test to compare those two models. And so just to try to fix these ideas, we will call two models nested if the reduced model is simply a special case of the full model. So as an example, with the model we've been considering, our full model said that each group had its own mean, and we can take that model and we can make the reduced model, that is our null hypothesis model, from this model by simply saying, let's let each of those individual group means be the same. So all the mu j's are mu, and in which case we get then the reduced model. So in ANOVA, that was how we had a full and a reduced model. In a few examples, in a few minutes, I'm going to talk about other examples where you can have this sort of full reduced situation that are perhaps not as obvious as with the ANOVA example. All right, so just to try to get at this idea of full and reduced, I'm going to write up here a table for what the assumptions, different means, residuals, and sum of squared errors are for the full and the reduced versions of the model. So in our ANOVA situation, our full model is that each group has its own mean. Our reduced model, we take that model, we fit a different mean for each group simply by taking the average within the group. We had those yj bars, and then we calculate residuals relative to those group means. So we take each of the observations, subtract the group means, and that gets our residuals. We take those residuals, we square them, and we add them up, and that is what we have for our sum of squared errors. Now in contrast, when we have the reduced model in this case says that the means are all the same. So now in order to estimate that mean, we're just going to take an average over all of our observations. So that's just y bar. Now when we're calculating residuals, we're just going to subtract y bar, right? Because that's the one mean in this model from each of the observations. So we have the yij minus y bar. So we've got a whole collection of residuals. we're going to simply square those up and add them up, and then we get our sum of squared errors under the full and reduced model. And you'll notice that these will be different because of our different means, right? We had in the full model, we have a different mean for each group. In the reduced model, we simply just have one grand mean for all the groups. Okay, so then the methodology that we use to construct an f-test, and this is really what the ANOVA table was doing before, it was just helping us organize the information. The organization, that organized way of doing things really did this. It calculated two quantities. It calculated the extra sum of squares. That extra sum of squares is the sum of squared error or residual sum of squares for the reduced model minus the full model. So if we just take those sum of squared errors for the reduced model, we subtract what we got for the full model. That is what we call the extra sum of squares. And this quantity is always going to be positive. Okay. Now the next step is we calculate the extra degrees of freedom. So we can take the number of parameters in the full model, we subtract out the number of parameters in the reduced model, and that gets us the extra degrees of freedom. One way to think about this is the number of extra parameters we have in the model. Okay, the next step is to calculate the F statistic. So we take what we got in step 1, divide what we got in step 2, and that is going to be our numerator. Then in our denominator, we have the degrees of freedom, not the degrees of freedom, we have the estimate for sigma squared in our full model. All right, now if the null hypothesis is true, then this is an F distribution where the numerator degrees of freedom are the extra degrees of freedom that we calculated in part 2, and the denominator degrees of freedom are the degrees of freedom associated with that estimate of sigma squared from the full model. So if you looked at the ANOVA table, you would just go to that line that has the sigma squared estimate on it and find the degrees of freedom. All right, so this is what we do to construct an F-test. I'm going to now go through two different examples of putting it into practice. So the first one is going to use, again, that mice lifetime example. Now, in that example, I didn't talk about it last time, but I've talked about it in a previous video. We had this NP group, and the NP group was no calorie restriction at all, not even the normal diet the mice get in the lab. And so in some sense, it's completely different than what we're trying to study. And so what we're going to try to do here is we're going to try to compare a model that allows NP to be different, but everything else the same, versus a model that lets everything be different. Okay, and so we have so we have the model here, just like we've had for the ANOVA assumptions before, but now our null hypothesis just says that all the means are the same, except for the group NP that I'm calling 1 here. Okay, so all the 5 other groups are the same, but the NP group is allowed to be different under this null hypothesis. The alternative just says that each group has its own mean. Okay, because J equals 1 was already different, so now now the alternative just says that one of those means are different amongst the collection of diets that are not NP. Right? If you think about this as a model, then what you get is something like this. So the null hypothesis says that you have one model for the NP group, right, that has a mean mu1, and then you have a different model for all the other groups with a common mean mu. The alternative model just says that each group has its own mean. So really, when you're conducting the F-test, you're comparing these two models. And now you'll notice that this is different from our ANOVA assumptions because the null hypothesis, it has a distinction for group NP, right? It gets a different mean and all the other means are the same. Okay, so as a picture, this is what we're talking about. The null hypothesis is the red bars. So notice that the NP group has a different mean, but all the other groups have a common mean, and that's why you get this sort of straight red line. The alternative model says that each group has its own mean. That's shown with the blue lines, where you have a different blue line for each group. You can't see the blue line in the NP group because the blue and the red line overlap. All right, so now we're not even going to try to do this calculation on our own, but instead we're going to use R to do it. The way that you do this in R is that you simply construct the two different models as regression models. So in this case, I had to construct a dummy variable for the NP group, and use that in a regression. So that's that first LM line, where we just have NP as the explanatory variable. So that dummy variable that indicates the diet being NP. The second model, our full model, just allows a different mean for each diet. So now we fit the two models, and now we can again use the ANOVA function. And that ANOVA function, when we put in two different models, will do all the calculations that we need to construct the this general f-test. So you'll see down here, we get a p-value for this f-test. Again, we want to check model assumptions before we go further. But assuming model assumptions check out, then we would think that, you know what, actually there's a different mean amongst those 5 other diets. Okay, so that was one example. Now we're going to do a second example of an f-test. This one is called a lack of fit test for linearity. And so this is where we're now going to sort of bring in this whole regression idea. So now we're going to consider two different models. The two models are an ANOVA model, where each of the groups has a different mean, and the other model is a regression model, where we have some explanatory variable, and we're going to assume that there's a linear relationship between that explanatory variable and the expected response. Now, in these two, the ANOVA model is our full model, and this regression model is our reduced model. And the way that we can see that the reduced model is a special case of the full model is simply to specify that those MJs must be on this line. That is the mu j, I said MJ, the mu j is equal to beta naught plus beta 1 times the xi. And now if we go and think about how many parameters we have for the mean, in the ANOVA model, we have 1 for each different group. So we have j, and in the regression model, we just have 2, beta naught and beta 1. Okay. All right, so again, small values indicate a lack of fit, that is against the reduced model. Okay. All right, so in order to do this kind of thing, you need to have multiple observations at a number of explanatory variable values. So as an example, here's a data set that looks at, I can't remember exactly what the time is, but, this is time since slaughter on some carcasses versus the pH. So, you know, wonderful topic here. But you'll see here that we have the 2 dots, right, for each different time. So we have 2 observations for each value of time. So 2 observations at 1, 2, 4, 6, 8, and 24 hours. And we're calculating the pH, or measuring the pH, on each of those different samples. Now, I put in box plots here because in some sense what we're thinking about under our ANOVA model is just to have a different mean for each of those different times. And so those box plots, especially the middle bar, represents that mean. Now you'll notice here on the x-axis, because we're not treating time as numeric, they are equally spaced. So we have 1, 2, 4, 8, or maybe it was 6, 8, and 24. We're just thinking about them as having different means. Okay. In contrast, we could have treated this as a regression problem. So now we've just taken those same observations, but we've now created a numeric variable for time, where now we can see a big spacing between 8 hours and 24 hours compared to between all the other observations. And so this f-test that we're going to do is going to compare looking at this linear fit to the data to the fit where we had each different group, in this case grouped by time, has a different mean. And so in this way we can try to assess whether we think that linear fit is a reasonable representation of the data or not. You can see right here, it looks like a pretty poor representation of the data. So our expectation is that we would get a small p-value to indicate evidence against this regression model. If we do the comparison in R, we fit the regression model, we can fit the ANOVA model. To fit the ANOVA model, we can do as.factor on our explanatory variable, and that turns it into a categorical variable. And then we do the ANOVA on those 2 models, and the results are here. And in fact, we see that p-value is pretty small, indicating evidence against the regression model. But of course, like always, we should go back and assess other model assumptions to see if there are other problems with the data before we conclude that it's simply that the line is not a good fit. Okay. So as a summary of these last 2 videos about ANOVA and these general f-tests, you can use this general f-test idea to compare full versus reduced models, right? They need to be nested. That is, the reduced model needs to be a special case of the full model. We showed in the previous video doing this for a one-way ANOVA f-test. In this video, we talked about a couple of different things, but we did sort of the general construction of f-tests, and we did a lack of fit f-test for linearity. All right, so the main thing I want you to get out of this is that these f-tests are really trying to compare two different models. And if you think about it that way, I think it will really help you out. I think in the next video, we're going to be talking about contrast within regression or the ANOVA framework. Hope to catch you there.